This is a lecture on 6-3, the central limit theorem. Now, the central limit theorem is a very important theorem, and we do start with the definitions, but instead of writing a separate definition handout, the definitions are here in your notes. They can be found under Files on Canvas. And what we need to start with is, what is a sampling distribution? Sampling distribution is a distribution that instead of individual results uses means of samples. So let's say I'm recording heights of people. So instead of recording an individual result, I'll maybe group them in, I don't know, group of 4 people, group of 10 people, group of 8 people, whatever fits best, and I'll record the mean. So I'll ask, let's say n is equal to 5, so I'll ask 5 people what your height is, find the average, and record that as one entry in my sampling distribution. So what we're going to do is we'll actually do this as part of the project. This will be one of the tedious parts of the project, and if anything, talk to me, I will guide you through that. The other another vocabulary word is sampling error. Sampling error is the difference between the sample measure and the corresponding population measure. This is generally due to the fact that the sample is not a perfect representation of the population, and if we get our results wrong, the chances are your statistician will say, well, it's a sampling error. And most important, the actual statement of the central limit theorem. It says, as the sample size n increases without limit, the shape of the distribution of the sample means taken with replacement from a population with mean mu and standard deviation sigma will approach a normal distribution. This distribution will have a mean mu and a standard deviation of sigma over the square root of n. There's actually one more vocabulary word that I'd like to stick right about here, is this piece right here has a name. It's called standard error of the mean. So one more vocabulary word there. So what I'd like to illustrate the statement of the central limit theorem so it makes a little bit more sense. So what we have is we're gathering individual results, and I really don't know how the distribution lays out, so maybe it looks like this, right? Skewed to the left, and it does have a mean. Where should I mean be? Probably right around here is my mean, and standard deviation. What the central limit theorem says is, if I take samples size n, now it does says that the n should increase without limit, which is not possible, so we have to stop at some point and actually fix an n. The sampling distribution, so this is individual. My sampling distribution if I will collect these samples many times with replacement, will actually look like this now. So I don't have a funny looking distribution that I cannot work with anymore. I have a normal distribution. Now the interesting part about this normal distribution, it will have a mean, which is mu, so the same mean, but the standard deviation, the ones that I can move left and right, will be sigma over the square root of n. That's my standard deviation. So I can do all of the stuff that I did in 6-2, except now I just have to watch out for that standard error, if I am talking about a sampling distribution rather than an individual distribution. So a good example is 6-13. Nielsen reported that children between the ages of 2 and 5 watch an average of 25 hours of television per week. Assume the variable is normally distributed and the standard deviation is 3 hours. If 20 children between the ages of 2 and 5 are randomly selected, find the probability that the mean of the number of hours they watch is greater than 26.3 hours. So let me kind of start with the beginning. The fact that the children are ages 2 to 5 has nothing to do with the problem. My first important number that I'd like to write down is the fact that the average is 25 hours per week. So this is my first mu, 25 hours. Assume the variable is normally distributed. So they actually gave me that the distribution is normal. So this is just much easier to work with. Assume the variable is normally distributed and the standard deviation is 3 hours. So they gave me that the standard deviation is 3. If 20 children between the ages of 2 and 5 are selected, so they actually gave me that my sample is of the size 20. Find the probability that the mean number of hours they watched, meaning the sample of 20. So we're not looking for individual results, we're looking for the results of a group of 20. As soon as you see a group of 20, you know that this is a sampling distribution. And you have to adjust accordingly. Your mu is 25, and we're going to label it like this. The standard deviation of the sampling distribution is now the original sigma divided by the square root of 20. So if we need to find the probability that the mean number of hours they watch television will be greater than 26.3 hours. So I'm looking at a 26.3 hours. It needs to be greater. So I'm right here. So what do I have? I have my normal CDF. I need the lower bound, comma, upper bound, comma, mu, comma, sigma. But I need the sigma of the sampling distribution, therefore it's 3 out of square, divided by the square root of 20. This is what you can put into your calculator. So distribution, normal CDF, 26.3, 1E99, mu is 25, sigma is 3 divided by the square root of 20. Your calculator will have no issue in calculating that as well. Push enter and you will get 0.026, and then I have a 3. So that should do it, just a little over 2%. I can do one more example. The average drive to work is 9.6 miles. I am reading example 6-14. The average drive to work is 9.6 miles, so they just gave me a mu. Assume the standard deviation is 1.8 miles. If a random sample of 36 employed people who drive to work are selected, so they gave me a sample. As soon as they gave me a sample, you know it's a sampling distribution. Find the probability that the mean of the sample miles driven to work is between 9 and 10 miles. So this is how you would write this down. the probability that the x is between 9 and 10. So I'm looking for a probability question. Is, if this helps, draw a curve. It is a sampling distribution, so regardless of whether they mentioned it's normally distributed or it's not, it doesn't matter, because you know that the sampling distribution will always be normally distributed regardless of the original distribution of the individual results, with a mean of 9.6 and this new sigma to be 1.8 divided by the size of the sample. So they're looking for results that are between 9 and 10. Notice the mean is 9.6, so I'm probably right around here, a little bit to the left of the mean, a little bit to the right of the mean, right, between 9 and 10. So it's a pretty good general picture. What I'm interested in is I'm doing in normal CDF because I'm looking for a percentile given the x. Lower bound to be 9, upper bound to be 10. The mean is 9.6 and a standard deviation of 1.8 divided by the square root of 36. So click distribution, normal CDF, lower bound 9, upper bound 10, mu 9.6, sigma 1.8 divided by the square root of 36. Paste, push enter, and what you will see is you will see a percentile 0.88603, so I don't need to bother with the rest of the significant digits. All of the problems in this book will look very similar, except for the last one, where they actually ask you for reverse. They don't talk about inverse norm in 6-3. That's my mistake. So we'll end this right here. And this is the end of 6-3. If you have any questions, please ask.